right, one moment. There we go. Well, hello. My name is Alexander Jeffrey. I'm from Boston, Massachusetts, and I'm a bio major here at BYU. I am today making a review video for the concept of enthalpy or entropy. I have trouble saying it, so I'll kind of hit it a couple different ways. But today, I just wanted to start off with a quick review of some important terms and some important concepts that we'll need to know in order to, get through this portion of the class. So the first thing is enthalpy is defined as the sum of the system's internal energy and the product of its pressure and volume. So a really great thing about this class is that all of our pressure is going to be the same. So that really simplifies when the process of calculating entropy, because otherwise we would have a lot more variables that we need to keep track of. That's because we work in this class in STP, standard temperature and pressure, which I really appreciate, especially now. We also just need to go over state functions. It's a property whose value does not depend on the path, but rather the specific value. Now, state functions the idea of a state function can be a little complex for some people, especially if it's explained very poorly like I might do. But the way that I think about state functions is the same way you can think about currency. So if I am going to Mexico and I have $5 and I go to Mexico and I exchange it for 10 pesos, that's the path. I'm going from $5 to 10 pesos. But if I take my $5 and I head over to the UK and I get 4 pounds, and then I throw over to I don't know, like China, and get 100 yen, and then make my way to Mexico and take that 100 yen and transfer it into 10 pesos. While the process were totally different, and one of them was way more complicated, the ending is the same. And in that case, we would call it a state function, because while the paths are independent, the outcomes are the same. And that's extremely important when we are trying to calculate delta H, which is defined as the change in enthalpy or heat. When delta H is positive, it means that product and the reaction have more energy compared to the reactants. So the reaction has gained energy, and that makes it endothermic. So these are just some concepts that I wanted to go over before getting into the kind of the meat of it, but we'll see how it goes. So let me just, okay, never mind. So there are 3 ways to calculate delta H. The first one is one that we've done before, we should be all pretty familiar with, which is Hess's law, where we take reactants, we go to intermediates, and we find our products. This is especially common for questions when we're manipulating reactions, when we're flipping them or multiplying them to add up to exactly what we want. This is a really, really precise way to get the delta H of a reaction. The next one is the delta H of formation, where we take our reactants, we go to pure elements, and then go to products. And in each of those steps, we measure the change in enthalpy. And as you can see here, we have the equation where products minus reactants give us our delta H of formation. And then finally, we have the third method, which is the method I'll be focusing on today, where we're focusing on bond enthalpy, where we take reactants, go to atoms, and end in products. This one is a switch compared to the delta H of formation that you might be more used to, where instead of products minus reactants, it's reactants minus products. Or it's bonds broken minus bonds formed. This is a good way to try and calculate the entropy when we're working with small atoms that we could fairly easily break down. So what is enthalpy in a bond? Enthalpy of a bond is the amount of energy required to break a bond. So sorry, let me restate that. Bond energy is the amount of energy required to break a bond. That's something we should be familiar with from earlier on in this year, because as we all remember, the more bonds you have, the stronger it is, and the shorter the bond, also the stronger it is. Long bonds and few bonds are not strong. And this is connected to the idea of bond enthalpy, where it's the amount of energy required to break 1 mole of bonds between those, those atoms. So, like I was saying before, there are stronger bonds, there are weaker bonds. Bond energy is affected by the difference in electronegativity and the number of bonds between the atoms. Triple bonds, of course, are stronger than double bonds, and double bonds are stronger than single bonds. Down here at the bottom, we have an example of these carbon-carbon bonds. The first one only takes about 347 kilojoules per mole to break apart. The middle one takes 614, and then the third one takes 839. So we see that there's this growth, depending on how many bonds there are, and that is standard throughout all of the different atoms and elements that we will come across. So how does bond enthalpy work? The way that we do this is we follow this 3-step rule. We break all the bonds down in the reactants, we break all the bonds down in the products, and we calculate the difference. Here on the screen, we can see kind of the flow diagram of bond enthalpy. We begin at part 1, where we have our reactants, we have our molecules, and we break them down into their parts, and then reform them into our products in an exothermic reaction. And then at the very bottom here, you can see that we calculate the difference, the delta H of our reaction, and that's what gives us really gives us our the number we're looking for, the information we're looking for. And this is, like we were saying before, this is an example of a state function, because instead of going, directly from $5 to 10 pesos, we're going around a little bit, but it can be easier, and also teaches us different ways to look at problems. So we're going to do this practice problem where we find the energy of this reaction. There are 4 steps for this, where the first thing we do is we draw out our bonds, we find their bond strengths, we write out our equation, and then we just plug and chug. Up here on the right, I gave us the needed bond energies. So the first thing that we're going to do, I'll switch to the next page, and then we will. I'll just give you a minute to pause the video, try and solve this on your own, and then we will go over it in the next slide. So. All right, I had a little technical difficulty, but I'll just work it into the pause between the question. But good job. I'm sure you did great. Now we're just going to go through how to get the proper answer to make sure that everyone gets these questions right on the exam. So I drew out what each of these molecules look like. And I think that for me, that's always the best step, especially if I'm really trying to make sure that I get every single one of these variables right. So we'll start off with NH3. So there are 4 NH3s. And we see that there are 3 single bonds around for each of these molecules. These bonds go from hydrogen to nitrogen. And we can just very easily look up on the last slide that bond is 391 kilojoules per mole. So the thing that we do for this portion of the equation is we say that there are 4 molecules of NH3. Each one of those has 3 bonds, and the energy required to break those bonds is 391 kilojoules per mole. And that equals 4,692. We then move to the next part of the reactants, which is oxygen gas, or O2. We can see that there is only 1 bond between these oxygens, but it is a double bond. So that will be stronger than a normal single bond. And we can see from the numbers on the screen that double bond is 498 kilojoules per mole to break. And because there are 5 of those molecules, then we will need to put a 5 before so we can multiply it through. And that comes out to 2,490. On the products side of the equation, we have 4 NOs. In the NO, there's a double bond between O and N. And because there are 4 of those, we're going to want to times, the bond energy by 4 in order to get the energy required to break it. And then finally, we have, I don't know if you can see this because I'm right in the corner, but we have water. And we can see that there are 2 oxygen-hydrogen bonds in water. And each of those bonds is 436 kilojoules per mole to break. So we're going to take the 6 molecules of water we make, times that by the 2 bonds, which are 469 kilojoules per mole. And that comes out to 5,556. Now we take these numbers, we put them into our equation, where we take our reactants. So that is the NH3 and the O2, and we pop those into our reactants bonds. And then we take our NO and our H2O and pop that into our products. We've got to make sure that we put in our minus, because otherwise we'll just be adding these all together and we won't be able to differentiate between the beginning and the start of the reaction, or the beginning and the start of the process. And if you do all that right, hopefully you came out to negative 802 kilojoules per mole. Sweet. Now, bond enthalpy has some limitations that are important to understand. First off is that the bond strengths that we're given in the chart are simply an average of all of the different ways that those bonds can be made. So it is not specific to the individual molecule that you're looking at. The second problem or the second limitation is that the calculations have to be seen as approximations because we're working off of an average. For more precise measurements, you should definitely use Hass's law or the entropy of formation. And then this is most accurate for elements in the gas phase of reactions because it interacts with solvents and that changes the bond to enthalpies. So you're going to want to make sure that you understand that this, the bonds are just averages, that the calculation is an approximation at best, and is most accurate when it's working with gases. All right. The next part of this lecture talks about fuel value. And I might ask a silly question, but what do you think? What is a better fuel for your spaceship, hydrogen or propane? Because I don't know about you, but I burn definitely a lot more propane, and I'm more familiar with that than I am with hydrogen. But if we wanted to ask, which had a greater fuel value, which was better for us to use, we want to find out the delta H of combustion of each of these molecules. And we can see below that the delta H of hydrogen is negative 286 kilojoules per mole, while propane's is 2044 kilojoules per mole. Now you might think, okay, boom, there it is. Propane's is much higher by a degree of 10. However, this is not taking into account the molecular weight of each of these reactants or these molecules. Now, the thing you can do is you can say, all right, hydrogen gas, that is 2 hydrogens. So we're going to look at our periodic table and be like, a hydrogen weighs 1.0079. It's probably not important to get all those decibels, but we're going to do it anyways because we want to get the best numbers possible. Times 2, because there's 2 of them. And that is going to give us, well, we'll just round it to 2, for the molecular weight of our molecule. And the thing we can then do is we can say that negative 286 kilojoules per mole over 1 mole. Sorry, let me rephrase that. We're going to do some simple math. We're going to take the delta H of combustion and divide it by the weight of our molecule. So the weight of hydrogen is 2 grams per mole. So we just simply divide 286 by 2. And then we do the same with our propane, where we say, okay, that's 2,000. Oh, okay, hold on. I'm just going to fix one thing, and then we'll get back to it. All right, we're all resumed. We need to just make sure that we had the, I wanted to make sure that you guys had the molecular formula for propane, which is C3H8. Now we can easily look at our periodic tables and say, okay, carbon is 12 grams per mole. And we'll times that by 3 because we have 3 of them. And then hydrogen is, 1 gram per mole per hydrogen. So we can just easily say that we're going to add 8 to that number, and then we'll divide our negative 2,044 kilojoules per mole by this number, and hopefully we will get that propane has 46.5 kilojoules per gram, whereas hydrogen has 143 kilojoules per gram of fuel efficiency or fuel value. So this helps us to know that hydrogen would be the best thing for your spacecraft because it is 3 times more efficient per weight than propane. And you can do this same equation for any combustible material to see, which is the most efficient, which is the best thing to use, especially if you're working with an industry or a group that is really cares about either efficiency and weight savings. So thank you so much for your time. I really hope that this was helpful, and best of luck with the rest of the semester.